Now we're going to look at the application called present value of a lump sum or present value of a dollar. Once again, you'll see there's a space here on the snowball sheet for a graphic depiction of that, and it's important to understand, I think intuitively, what's happening here. You know, we've all seen snowballs roll down the hill, or at least we understand the concept of that and why it is a snowball gets larger and ever larger if it rolls down the hill. Present valuation is a different animal. We really don't observe that in nature. But imagine this. Let's say that you have taken a snowball at the top of the hill and you push it down and it rolls down. Of course, gets larger as it does that. But then once it gets to the bottom of the hill, you take that video that you have made and you run it backwards. And so that snowball at the bottom of the hill in the video rolls back up the hill and of course gets smaller. Matter of fact, if you think about visually what's happening, that snowball as it rolls down the hill sort of leaves a trough, doesn't it, as it attracts snow. And when you roll that video backwards and it goes back up the hill here, that trough is filled in, it leaves a nice smooth path behind it. It's a pretty good metaphor, I think, or explanation of what's happening here. Because what we're doing in present valuation, by the way, the process is called discounting or uncounting. You know, we had compounding with a snowball rolling down the hill. Now we have discounting with a snowball rolling back up the hill. But it's as if we are taking the snowball and then shaving snow off of it as it rolls back up the hill and it gets smaller. And of course, this is still referred to as a future value, and this is a present value. Present valuation really has far more applications in finance than does future value of a dollar. Because all valuation really it involves estimating future returns from any investment and bringing those back by discounting them to the present to determine what the investment is worth. And so we're going to shortcut this. We've got the mathematical model here, but that's for the sake of the purists who want to see some connection, I guess, to the sciences or whatever. But in fact, I'm going to be talking about this in terms of what I've called the usable form. Present value equals future value, and then N and I. And again, I want to just make sure I want to emphasize to you, we're not going to take future value and multiply it by these factors here. Okay? This maintains the appearance of the mathematical model, which I think is helpful as you build problems, as you solve problems using these building blocks. But we're not actually performing any multiplication between these. These are just identifying the inputs, the calculator inputs, while maintaining that appearance of the mathematical model. Let's look at this application here. Assume someone offers you an investment costing $10,000 that will pay $20,000 5 years from now. If your required rate of return for this investment is 14%, is it a good investment? Now, there are actually two ways to solve this problem. Let's solve it probably the most basic way. The two ways to solve time value of money problems are like this. You will estimate or you will calculate the present value of the investment and compare that to the cost. If it's worth more than it costs, it's a good investment. If it's worth less, it's a bad investment. Okay? The other way is to calculate what we call the internal rate of return. Okay? Compare that then to the required rate of return. And if the IRR exceeds the RRR, it's a good investment. Otherwise, it's a bad investment. Let's solve this problem first of all by solving for the value, the present value of the investment. And so what we would do here is to take that $20,000 that you are going to receive in 5 years. N is equal to 5. By the way, I guess I should walk you through these definitions here. Future value is $20,000. That's the amount you would receive in 5 years. It says the required rate of return is 14%. We're going to assume, unless told otherwise, that any compounding or discounting occurs on an annual basis. That is, that it doesn't say here. So we're going to assume that's a 14% annual rate of return. And interest is, in this case, discounted annually. So N is equal to the number of years, 5, and I is equal to 14%. Now I'm going to use percent sign here because now that we're using the calculator to do our work, there's no real reason to use the decimal form of these. So let's take that $20,000 and input these amounts to the calculator. That I'm going to clear out the calculator first of all. Wish I could show you this. I'm not sure if that'll even be of much help to you, as small as it is. But $20,000, well, let's see, second, clear TVM, clear out those registers there. Now, $20,000 is a future value. N is 5. 14 is I. Okay, I've got my inputs in there. Now, compute present value. And it shows 10,387.37. 10,387 is certainly close enough for our purposes. Now, by the way, some of you might note if you're solving this on your TI BA2 Plus or one of the emulators that are available for just a few dollars through the Apple Store, that in fact when I solved for that, I put this in as a positive amount and this came out as a negative amount. It's not to worry. What that means is you have to understand how the calculator is understanding these values. The calculator understands the notion of investments. It's really good at calculating these values. And if you propose a situation where you get $20,000 in 5 years, and you say, give me the present value of that, it's going to say, oh, then that really represents a negative. You would have to pay, in other words, or be willing to pay, in this case, $10,387 in order to obtain that $20,000. So the investment involves paying money today to receive money in the future. And so if you put in $20,000 as a positive, it'll give you this present value as a negative. Now, by the way, of course, if you put this in as a negative, it'll give you this as a positive. One thing to note is that in any investment, you've got an investor and you've got an investee. Just like with any loan, you've got a borrower, you've got a lender. Okay, you've got a buyer and seller in any normal commercial transaction. So it's just something you want to note. It'll become important for us later on as we solve certain problems, because we'll have sometimes both negative and positive cash flows associated with an investment. And we'll have to specify those and be careful about that so that we designate money going out as negatives, money coming in as positives. But now, how would we use this particular tool here? We haven't, in this particular case, it says someone offers you an investment costing $10,000. And so you can buy this $20,000, this cash flow of $20,000 in 5 years. You can buy it today for $10,000. Well, we can't compare that $10,000 directly to the $20,000. That's the proverbial apples and oranges. It's like U.S. dollars and Australian dollars. You can't really just compare those on an equal basis. But this 14% here is important. It's like a foreign exchange rate. If you had the exchange rate between U.S. and Australian dollars, you could make the judgment about what Australian dollars are worth in terms of U.S. dollars. What this discount rate here represents is more or less an exchange rate between money today and money tomorrow. Okay? So what we want to do is just recognize that $20,000 is not that's not like 20,000 of today's dollars. Bringing that $20,000 back, converting it to what it's worth today, that's $10,387. So the question is, how do we evaluate this as an investment? Is it a good investment? And the idea is that you've decided it's worth $10,387. If you can obtain it for anything less than that, it's a good investment. Well, this investment cost $10,000. So this is a good investment. It will create value. That is, this project has a net present value of $387. Remember the notion of net present value? Present value minus the initial outlay gives us NPV. So 10,387 minus 10,000. This investment will create value. It's a good investment. Well, the other way I mentioned that we can solve problems like this is by calculating the internal rate of return and comparing that to the required rate of return. So let's reformulate this problem. Tell you what, I guess it's easier just to go ahead and get rid of this. In this case, what we're going to do is specify that this is the present value. Now in this case, it's the present value of the cost, okay, what we would have to pay for it. So we're saying we would pay $10,000 to get $20,000. And the question then is, what rate of return is implied by that relationship? So we go back to the calculator, and this again is, as we'll see, you'll see why it's second, clear TVM, clear out those registers. And then it's important for us to realize that, one of these is a negative and one's a positive. From the investor's perspective, this is a negative. They're paying this to get this. But again, just as an aside, realize that in every investment transaction, somebody is getting that $10,000 with the obligation to pay $20,000 in 5 years. Okay. So let's put in here $10,000. That's a negative. That's my present value. 20,000 is a positive. That's my future value. 5 is N. And I'm going to compute I, but let's talk just a moment or think just a moment about what we expect the answer to be. This is a good investment, right? It will create value. It's worth more than it costs. And these two approaches, the present value or NPV approach and the IRR approach, are really, as I've said, kind of joined at the head. They're going to give you the same yay or nay. So if it was a good investment by the present value approach, it's going to be a good investment by the IRR approach. Now, what does that mean? How do we know a good investment using the IRR method? And the answer is, a good investment is one where the IRR is greater than the RRR. So we would expect, since this is a good investment, the IRR is going to be greater than the 14%, that we had as a required rate of return. So now I'm ready, drum roll, let's see, 14.87%, or I is equal to 14.9%, rounded to the nearest tenth of a percent. And I would like for you to take your answers out to the nearest tenth of a percent. So 14.9%. So here's an evaluation. And I'll emphasize this more in class, but I want to, not for you just to crunch the numbers, but to also let me know that you know what you found. In this particular case, if we were asked to evaluate this investment by the present value approach, I would say this is a good investment because it's worth more than it cost. It's worth $10,387. It cost $10,000. It will create value of $387. By the internal rate of return approach, this is a good investment because the IRR is greater than the RRR. IRR 14.9%, RRR 14%. Okay, so that's a good investment. All right, now that's the application. We'll see a lot of this later on because most of our investment decisions are going to involve estimating the future returns from the investment, whether that's a particular piece of machinery or it's a stock or a bond or a business. Estimate the future returns, estimate an appropriate required rate of return. And by the way, I say when I estimate future returns, how much you're going to get and when you're going to get it, okay? How much and when, and then estimate an appropriate required rate of return. And then you can evaluate that investment by either of these two methods or both of these two methods.